Hello everyone. Today is the 38th day of Leetcode 75 challenge. Let's begin with the 38th question. Question 236, lowest common ancestor of a binary tree. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. So you are given the root of a binary tree. You are also given two nodes P and Q that exist somewhere in the tree. Now our task is to find the lowest common ancestor of these two nodes. Fine. So suppose there is a tree. Okay, this is a tree, and they say that P and Q are two nodes which exist somewhere in the tree. For example, one P is existing in this node. Suppose Q is existing in this particular node. Fine. Now, according to the definition of LCA, so we have to find the LCA, right? So, what is LCA? The lowest common ancestor is the lowest node in the tree that has both P and Q as descendants, where a node can be descendant to itself. Okay. So what does that particularly mean is that uh, since P is here, okay, so what is the common node between both P and Q? Is this the common node between P and Q? No, because this is a root node, right? Fine. And is this is the common node between P and Q? No. So if you could see, this is the common node, right? Because if you observe, this is the common node. Let it be R. Fine. This is the common node between P and Q. So this becomes the LCA for this particular for these two particular nodes given. Fine. Another line, this is it is said here where a node can be a descendant to itself. It basically means suppose this is the given tree to you. Fine. One P is here and Q is here. Fine. Now for this particular tree, the LCA node would be P itself. Reason being, if you could read the definition again, it is the lowest node in the tree. Okay, this is the lowest node in the tree that has both P and Q as descendants. Okay, if you take this node, descendant of this particular node is Q, correct? Also, where a node can be a descendant to itself. So, and P itself is the node, right? So it becomes descendant to itself, and this Q is the descendant for this particular node. Fine. So this is what an LCA is. Fine. We have to basically find a lowest common node which contains both the P and Q in it as a descendant. Fine. So you can start from the root and explore the tree to find where P and Q are located. The LCA is a node which both P and Q can be reached. Fine. Okay. So basically, this is the node. In other words, you could say that this is the particular node from where you could reach P and Q. Fine. Either directly through its subtree. Fine. So this is about the problem explanation. Constraints of the problem is the number of nodes in the tree is from range 2 to 10 to the power 5. The node value could be from minus 10 to the power 9 to positive 10 to the power 9. Fine. All node values are unique. Okay. All the node values are unique here. P and Q are never equal. The values cannot be equal. Fine. And P and Q will always exist in the tree. So these are the main things which we should know. So, so I hope you understood the problem explanation and the constraints. Now let's move to the next slide. Now let's understand the input output of the problem. Fine. So if in this given particular tree, P is 5, where is P5? It is here, right? Where is Q1? It is present here. So according to the definition of the LCA, we have to find the lowest common ancestor, basically the node from where we could reach P and Q. Fine. So if you could see from here, 3 is a LCA or the lowest common ancestor for 5 and 1. Fine. From 3 we could reach both 5 and 1. So this becomes the uh, we could say ascendant to their descendants 5 and 1. Fine. That's why the answer for this particular 3 is node is 3. Now for example 2, if you could see, we have this particular node tree and P is 5 again, Q is 4. Okay. Now what? Now, from 3, can you reach 5? Yes, we can reach 5. Can you reach 4? Yes, we can reach 4. So one of the answer could be 3. Okay. From 5, can you reach 5 itself? Yes. From 5, can you reach 4 itself? Yes. So 5 becomes the another answer. From 2, can you reach 4? Yes, but can you reach 5? No, because we have to go upwards, right? But in the LCA, we have to go downwards. Fine. So from 1 also you cannot do 8 and 0, right? So from here, you could see the lowest one is 5 in this case. Fine. So you return 5. Because if you remember, the node, suppose the node is also a descendant to itself. Fine. So keep that in mind. That's why 5, and this becomes the one of the LCA, or not one of the LCA. It is the LCA. Fine. So 5 is the output for this particular example. So I hope you understood this input-output explanation. It was pretty easy and straightforward. There's nothing to make much complex about it. Now let's move to the next slide. To understand what problem is asking, we should build up the intuition to the problem. Fine. So let's start by understanding the goal. So you are given a binary tree. Let me draw one. You are given nodes P and Q. Let 6 be one of the node, and let 5 here be one of the node. Fine. Let it be P and let it be Q. Okay. Our task is to find the lowest common ancestor, the lowest node in the tree that has both P and Q as descendant, including possibility of being descendant of itself. So I hope you understood this particular line. I have explained it earlier also. Let me give some random numbers, 1, 2. Okay. So I've given some nodes to it. Now, if P or Q is not in the root, then the root itself is the LCA. Fine. For example, if P or Q is not present in the root, the root itself becomes the LCA for the particular thing. Right? But since a node is allowed to be a descendant to itself, so we return that particular. Basically, they are trying to say that in this LCA problem, if 2 and 3 we have to find, then 2 becomes the LCA, right? But if this case was not given, then it will return the root node. Fine. Since this case is given, so you don't have to beat your head around the bush for the particular thing. When we comes to the part, if P and Q are the same node, then LCA is simply that node. But here P is never equals to Q, so we can just ditch this particular thing and this also, right? So you understood this particular problem. Now, what could be the brute force which can come to our mind, right? It could be that what way do we store all the paths from root to P and Q, then compare them to find the last common node. So what does this particular mean? Or let's think that okay, let's take out the path for from root to P, okay, root to P and Q differently, fine. So directly going to the tree, if you would see the path from root to P is 1, 2, 3, then we come to 6, right? 1, 2, 3, then we come to 6. Then for 5 it is 1, 2, and 5, right? Okay, so this is the path, correct? If you take out the path from the tree. So if you could see 1 and 1 are matching. 1 and 1 are matching, fine. 2 and 2 are matching, fine. But the next node 3 is not matching to the 5, right? So this particular thing tells us that till here the path was same, right? Common sense. From starting to 2, the path was same till here. Then the path got separated, fine. So what does that mean? That means that 2 was the last point of contact for both of the nodes. Okay, so basically the tree was coming this way. So the parted way is here, fine. So this is 2, right? So if someone will ask you that I'm coming from P and I'm coming from Q, so where should we meet up? Fine. Then you will say there is a turnabout or turnaround after some kilometers. There we should meet up, right? So that turnaround is the common point for this particular meetup place for P and Q, right? So similarly here also, the path from the road or the home was common till this turnaround, and then it got separated, right? So this particular thing becomes the common ground. So this is the LCA in this case, right? So here also, if you see 3 and 5 are the parted ways, but 2 is the last point of contact for them. So this becomes the LCA of the particular P and Q. So here also, if you could see in the tree, 6, 3, 2, okay, and 2 and 5. So from here you could see that first 1 is one of the common path, LCA, it could be one of the, right? Then 2 can be one of the. So but the lowest from 1 and 2 is 2, right? And you could also see that creates a common ground here. So that's why the output for this particular uh, P and Q LCA is 2, right? But the issue is here is that this is a completely correct solution, but the time complexity could be, but here it is a kind of inefficient also, because the time complexity for this particular would be O of n in worst case plus O of n in worst case. Because why 2 times? Because we will call the functions 2 times for path 1 and path 2 also. And space complexity also is extra other than recursion, which is O of h plus O of h. O of h, why? H is the height, right? So the path would be only in the way of height, correct? That's why. So this becomes a kind of inefficient solution because this time complexity is O of n at the end or in the best case, it could be O of H if you just get it in one traversal in the height, just iterating the height part rather than traversing the complete tree. The space complexity is O of H. So to reduce this particular thing, we have to look for something else, right? So that we don't use this space complexity, which takes the extra space rather than the stack space, which recursion usually takes, and time complexity can also be reduced, right? So we have to aim for an optimized recursive approach that traverses a tree only once, okay, and makes the decision during the recursion itself. Now let's visualize the efficient process. Let me draw on the tree first. Okay, so I have drawn the tree. Okay, now let's understand. Now we begin at the root and check if it matches P or Q. That's a simple thing. We will always start with the root node. Fine. Now we will go towards the descendants or the child nodes, right? To come here. If you okay, I forgot to mention something. Let P be 5. Okay, and let Q be 7. Okay, for this case. So what you will do, you will go and search for P and Q while iterating the tree, while recursively iterating the tree. Fine. You came here, you came in the fourth node, you came here and you saw, okay, we have a node which is 5. Okay. So we as soon as we got a node, okay, one of the nodes, which is 5 in this case, which is equals to P, what you could do, you could just return it, right? If you just return it, you have 5 with you, right? Okay. This traversal for this particular node is done. Fine. Now, if you come in this particular direction and you check, okay, we have 7 also, right? Then you return this particular thing. Okay. And in this particular node, you see that, okay, you have both the P and Qs. Then what you do, you return this particular two. Okay. Now I have just mentioned it in very short form or in a shorter way. Let me just elaborate it in much uh, efficiently. Okay. So what we do, we begin at the root and check if it matches P or Q. Fine. If it does, we return it. Okay. Because the node is one of the targets and could be the LCA, correct? If not, we recursively search the left and right subtree for P and Q. Fine. Now there could be three possible cases. Fine. What happens is here. Now let's make this clear. Suppose you are traversing towards the downward, okay, towards the descendants. You got 5 years. Suppose you got 5 years. So let suppose you got 5 in your while doing the left traversal. Fine. But in this case, you got it in the right traversal. This fine. So let me write it right to make it justified. So you got when you try to traverse right, right? So you stored that value here. Okay. Now left is null. Okay, we have two values. It is null. Fine, no issues. Now what happens is that from here you got 5, you checked for left and right, so nothing, so you return 5. Now for this particular node, you already traversed left, right? So you for this particular value or node, you have null with you, correct? And for this particular right side traversal, you have 5. So since this is null, you will return 5. Okay. So for 4 returns 5. Okay. Now 3 has from the left hand side 3 has 5 and from the right hand side it is null, right? So since right hand side is null and left hand side it is 5, so it returns 5 back. Fine. Now we are in 2 and it 3 returns 5 from the left hand side. Fine. Now you went since right side of the true is not traversed, now you will traverse towards the right side. Fine. Came here, you came here, you saw we have 7. So the left you got from the left you got 7 for the particular node. Okay. For the particular node. Okay. For this particular node, from the right side you got 7. Right. Then what you did, you checked for the left and right. Since you didn't have anything, you returned 7. That's great. In 6, now 6 is returned with value 7. Now what happens? 7 returns back from the left hand side. Okay. So from 6 from the left hand side got 7. Fine. Easy. Now 6 goes to the right hand side traversal since it is null, so it returns null. Okay, so 6 returns null from the right hand side for this particular node. Fine. This left and right variables get updated for every node. Okay. If you have the understanding of recursion, it is not much thing to be explained fine here right now. Okay. So this is what now 6 has left as 7 and right has null. So it returns left back to the parent call. Fine. 6 returns 7. Great. Now if you see, we are back to the 2, right? Now from now 2 has from the left hand side, if you observe, it is 5, and from the right hand side it is 7, right? Since we have both the left and right values, that means we have found the P and Q both. Okay. And the currently in which node we are standing is of course the LCA for those particular P and Qs, right? So what you do in this case here, you just return the root. So it returns 2, okay, to the 1, right? And it goes here, it's similarly the same thing, but if you have understood till now, it will of course return null back, this complete left right subtree, fine, right? So root has only 2 from the left hand side, okay, let me write it here. It has 2 and null, okay, the root 1. So since left it is not null, so 1 returns 2. Those 2, so for this particular thing, 2 becomes our answer, fine. If you also observe, 2 is the common path for this these two particular P and Qs, right? So this is what is written here. Three possible cases. If both left and right return non-null values, which was in this case, right? Then we just it means that P is found in one subtree and Q is found in another subtree. So the current node is LCA. This is a common thing which we got here, right? Let me clear this up once. Okay. Now, if one side returns non-null value, that means both nodes are in that subtree. Fine. So here, if you have observed this, let me clear this up. I think you understood how this is working, right? Let me clean this up once to make it to give you a summary of the intuition. So what it say? If one side returns non-null value, if you remember that this returned, this had one side null and other side non-null value, right? So if one side returns non-null value, which we did, that means both nodes are in that particular subtree, right? If left is none, here left is null, so we try to return, but right is not. That means we didn't find either P or Q in the left subtree. Fine. In the left subtree, we didn't find anything, but we did find one of them in the right subtree. Correct? So there could be a reason that only in the left subtree there P and Q could be available, right? But here it was P was only available in the right subtree. So that's why we wrote here one of the P and Q, right? Since it was present in the right side, so we return the right result upward, and it may be the LCA or part of the path to it. It may be the LCA because if suppose these are the two nodes, if you remember, and I return this particular left, right, and here also the left is there, so this becomes the LCA, right? That's all. That's why I said it may be an LCA. Now coming back. Similarly, if right is none but left is not, here if you could see, right value for this particular thing was null or the right subtree was null, but we had the left value. So we returned the left because we find one of the P and Q, one of the P and Q, and that could also be an LCA for the particular subtree. Fine, one of the P and Q. So we return left upwards for the same reasons. Now, if both sides returns null, so for example, this is also null here and this is also null here, right? We don't have P and Q here. So when we return null value so that we understand that we didn't got anything from this particular subtree, right? This ensures that we explore all the paths, always return the correct ancestor as we backtrack. So this problem or this intuition is basically built up upon backtracking itself. You're just writing the recursion going downwards, just in simple explanation. If you don't have the left, if you didn't find anything in the left subtree and you find something in the right subtree, either it could be P or Q, you just return that particular thing, right? But if you find both in the left subtree and the right subtree, or basically you have both P and Q found in your variables from the right and left subtree, you return the particular node where you're standing at. Because this is the LC, of course. We have already seen in the intuition part. So I hope you understood this particular thing. But how we can simulate this, right? How we can do this, right? We can just use a simple recursive DFS starting our route, right? At each step of the recursion, we can check if the current node is null, right? This is very simple. Suppose this is a tree, nothing to think about. Recursion is very easy. If the current node is null, suppose this is null, right? This particular thing is null because it doesn't have any child. We just return null. That's all. If the current node is either P or Q, we return the node, right? If suppose this is P, so we return this. Okay, as we understood previously. We then call the recursion for both left and right children. Always in recursion, we call the left child or the left recursion first, then the right recursion. Fine. So this is what we call the recursion call. And if you don't know about recursion calls, please have the understanding for that and then come back to the video. Once you get result from both the subtrees, which if both are non-null value, we current the node in the LCA. Basically, for this node we call the left subtree and right subtree, right? If from the left we got non-null values and from the right also we got non-null values, then we return the root of the particular node. Fine. Okay. If one is null, suppose this is null, you got left side null and the right side not null. So you of course return the right part or the non-null value towards the top. Fine. This way we avoid storing paths or making redundant calls. Fine. What we figure out? We figure out that the brute force tracing method was high space and time complexity due to path storage and comparison. Right. This is what we saw in the brute force, that there was space complexity was also extra used and time complexity was also being extra. Right. The recursive approach efficiently explores the tree in one pass of DFS. In the optimized one, it leverages the return values of left and right recursive calls to make LCA decision at each node. At each node, we are trying to make a decision, right? We're passing back, and this is basically using the concept of backtracking here. The key insight was if both sides of the current node return valid nodes, that node is lowest common ancestor, right? If the left call and the right call both return something, what we saw from the previous part, that means that the node for which this left call and right call was done, this is the particular LCA for the particular nodes, right? I hope you understood the intuition. Now let's move to the next slide. Now, since you got the intuition of the problem, let's look into the approach how we're going to solve it. First, we will start by handling the base case and define the recursive functions. If the current node is root, is none. Fine. We return the none since no nodes found here. Of course, if this is the leaf node, for example, this is the leaf node, and leaf node's left is always null and right side is also always null, right? So in that case, we will just return null value. That's the simple thing which we can do. The current node is equal to P or Q, we don't know, but it is equal to something between P and Q, right? So we return the root itself, right? This means that we found one of the target nodes. If P or Q is the root, LCA is the root itself. So it will be basically if root is null, right? Or something like if P is equals to root value, root dot B, okay? Or let it be a root, I think it will be written like this only. Root equals to, sorry, not root, let me write it again. Okay, something like this only. Root dot val, here also val, equals to Q, right? If any of these things becomes true, right, we just return the root itself. If it is null, this root will be null. If it is equals to P, it will be P. If it is equals to Q, it will be Q, right? That's the thing. Because if we find P or Q or each reach a leaf, we return immediately and further and stop the further recursion. That's why, right? Because if you find a P here, why we will go further down, right? That's right. Now recursive search for left and right. This is basically recursive calls you will do for left tree and right tree. That's all. Fine. Now step 3, determine the lowest common ancestor based on the returned result. This step is very important, which we will write. Okay. Now one thing is that if both left and right recursive calls returns non-value. So basically it is, let me write it like this. If uh, right is null, suppose right, else let it be left equals to null. Fine. And else it will be return root. And here we return right, here we return left. So this is what we did previously. If we check that if right was null, we used to return left, if you remember. And if left was null, we used to return right. If both were not null values, we used to return the root, which was basically the LCA. So this is what is written here. If both recursive calls returns non-null values, this means P and Q are found in different subtrees of the root. So root is the lowest common ancestor, return the root. If one of the side returns a non value, basically these two conditions, if left is not none, return right. It means both P and Q are in the left subtree or the left subtree return LCA. Fine. Return left to propagate what results of the recursion stack. If the right is not none, it means both P and Q are in the right subtree, right? And or this subtree returns LCA. This could be the two things. So we return a right. Because if both side contains P or Q, current node is LCA. Otherwise, propagate the not none value towards the upward direction. So this is the important thing. I wrote the code here. Okay. Now, final output is what is the final output is that at the step 4 we return the final output. The recursion unwinds, fine, recursion is complete. We return the node that is the lowest common ancestor of P and Q. So when the function which we will write will return the node at the end, fine. That is the LCA for our particular given root node. This will be the first node where P and Q are found in the different subtrees, where one of the node is the ancestor of the other, fine. That's the thing. This is just the returning of the value, that's all. So I hope you understood the approach explanation. Now let's move to the next slide. The code is the exact copy of the approach we discussed. Let's understand it line by line. So if you could see what I have done here, if root is none or root equals to p or root equals to q, just return the root, fine, towards the upward direction or backtracking. Then we call the left subtree, then we call the right subtree. And this left subtree goes until this base condition is reached, and similarly for the right. Okay. Now, what happens after every call is done? We check if left is none, fine, we return right. Okay, if right is none, we return left, otherwise return root, we got the LCA, right? Suppose, and if you are not yet confused with this particular part, why if left is none, we return right. Suppose here you got nothing from the left, okay, but you got something from the right. So of course, for this particular node left subtree, there was no P or Q, okay, anything between them. But for the right subtree, you got something, correct? So for this particular node, you got something from the right. So you return the root of that particular so we return from here, fine, whatever root you got here, the value. So this particular thing returns this from here, right? So for this particular node, this is the left subtree, correct? For this was the right. For this node, this was the left. So it will check, okay, from left I'm getting something, uh, so we return, so we will take it. Similarly for the right, if you get something here, that means for this particular node you got something from the left and get something from the right. That is why this condition is done, written here, fine. And the time complexity comes out to be O of n, because we are iterating in the one pass itself, and usually the space complexity is O of 1 if you take the recursion stack space, that is O of h or O of n, in this case any of the one, right? That is a different thing, but externally you have not used anything, that's why O of 1 is there, fine. I hope you understood the code explanation. Now let's move to the next slide. Now since we have the understanding of the code, let's look at a dry run of the example. Let me draw down the tree first. Okay, so I've drawn the tree here already. Now for this particular example, P is 5 and Q is 4. So it is P is 5 and Q is 4. P and Q. Okay, great. So, so I brought down the code also if in the left hand side if you could see. Okay, now let's do the dry run. So according to our problem, we started with the root is none. So we can see that root is not none. Our iterator is here. Neither it is equal to any other things, right? So we call the left subtree. We come here. Great. We see that for this the root is not, for this root is equals to P, right? So what we do, we return, for this particular case we return 5, fine. So this is returning 5. Left call is done, correct? Now we call the right for this particular node, correct? So we come here, we're standing in 2. So 2 is neither the none, either it is equals to Q or P, fine. So we call the left subtree for this, we check it is 7. So it is also not equals to the P or Q or not the null, fine. Then if you check for the left, it returns null, right? Because we don't have the left subtree for this particular leaf node, so we return none from here for the root. Then here also it checks it is null, right? So it also returns null. So this particular node returns total null in above node or to its parent node. Fine. Let me clear this up. So it completely returns null. Fine. I hope this is much clear. Now this left call is done for this particular node. Now you come for the right call. To come here, we check, okay, 4 is present here, which is equals to Q. So we return root. So we return root directly without going further down. So it returns 4 here. Now the recursion goes back. Now it is in 2. Okay. Now it checks that, okay, left is none in our case. So we will return right. So this node returns right, which is 4. Okay. Now we come back to this particular call. This was done for this particular call. Now we come here. We say left is none. No. Right is none. No. So we return root, which means that both left and right has some value. So we return root. So root for this is 5, right? So it returns 5. Now we come back to this particular node. We go to the right. We check it is none. P or Q? No. Then you come to the left call. It has something? No, right? Then you check for the leaf node value. Since it is a leaf node, so it will of course return none. Fine. And for then you come back to this particular call. You see it is 8. It is also not equals to P or Q, but it returns none though because it doesn't have any values. So it returns none. Now this returns the none. Okay, back. We have none here, none. Fine. Now this three node from the left it is getting left is not null here. If you see left is none, no. Right is none, yes. So it returns left. So this particular node returns null left, and the value of left was 5 in this case. Right. So output for this particular example is 5. I hope you understood that right, and it was pretty easy. There was nothing complex about it. If you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach and the code. After that, do a dry run by yourself and 2 3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Now let's move to the next slide. Now, since you're familiar with the problem and the solution, let's move to the lead code and code the solution. So first, base case was if root is none, or if root equals to p, or root equals to p. Now you might be wondering why it is not root dot val, because if you could see, we are passed with the root itself, not the root val. P and Qs, they are passed with the tree directly, right? That's why. Then we return root. Otherwise, we call the left. Now, one more thing is there. Why you might be having question. It might be that why are you not calling the recursion directly in this manner, right? Because this is good way, but this won't be able to store any values of the left call and right call. So to store the values for the left and right call, we have to store it somewhere, right? This variable stores the particular value so that we could compare it further, right? That's why. Otherwise, if we call it directly, we won't be able to store anything, right? So store, copy. It is self-taught. Self-taught. Right. Great. Now we will check if left is none, return right. Now these variables are coming in use, right? Else if right is none, return left. Else both have some values, so we return root. Now let's try submitting. Okay, the sample test cases have been passed. Now let's finally submit the solution. We have successfully submitted our solution. Now the code of the problem is available in my GitHub repository. You can find a link in the description. Thank you everyone.